In this lecture, we are going to understand locks in more detail. So what are locks? We've seen in the previous lecture that anytime multiple threads are accessing shared data, race conditions can happen. Right? Suppose you're incrementing a shared variable called balance. Multiple threads can increment it concurrently and it can result in incorrect values of the variable. So in such cases, we need to use a special lock variable in order to provide mutual exclusion, right? So let's call this lock mutex, and you declare this lock variable, you call the lock function on it, you access your critical section, and then you unlock it, right? So this piece of code between the lock and unlock is called a critical section. And a lock ensures that only one thread is executing the critical section at a certain point of time. So the first thread that succeeds in acquiring the lock, that is called the owner of the lock. And as long as some thread has locked the mutex, all other threads are going to block at this point, right? There can only one thread can proceed, and all other threads that try to lock will have to wait. So the lock function does not return. It blocks until some thread is executing in the critical section. And once the thread unlocks it and finishes it, then another thread can go ahead and enter the critical section, right? So this lock and unlock functions on the lock variable give you that semantics. And these locks are implemented by several libraries. For example, the pthread library has different types of locks that it provides that user programs can use in order to guarantee mutual exclusion and atomicity in the critical section. So now that we know how to use locks, the next question comes up: how do we implement these locks, right? So there are a few goals of any lock implementation, right? So first thing is your lock and unlock functions should guarantee mutual exclusion. This is obvious. Other goals are something like fairness. If there are multiple threads that are trying to get into the critical section, all of them should get a turn, right? It's not like only one thread always succeeds in locking and the other threads are starving. That shouldn't happen. Any lock implementation should guarantee fairness, and it should also have low overhead. So all the threads that are waiting to lock should not spend too much hardware resources, either CPU or memory, in order to acquire, release, and wait for a lock, right? So fairness and low overhead are sort of nice things to have, but mutual exclusion is the most important one. It is not negotiable. And there are several places where you need to implement locks, right? So for user programs, you might need to implement locks because something like the pthreads library gives you the API, the functions for lock and unlock, and it needs to implement the logic for that. At the same time, you also need to implement locks inside the operating system code, right? The operating system, for its own data structures, it needs to use locks, right? So in the next few slides, we're going to see how locks are implemented. And remember that implementing locks is not just a software operation. You also need small amount of support from the hardware. With support from the hardware, the operating system implements locks, both for user programs as well as for itself. So one small thought, right? So if you remember the example of the critical section, what happened? A thread got interrupted at the wrong point of time, right? If you remember the counter example, the value of counter was read into a register, but before it could be written back into memory, it got interrupted. So is it enough if you just disable interrupts, right? When you're making changes to some critical section, is it enough if you just stop interrupts and ensure you run continuously on the CPU? Is that enough? For example, can your lock function simply be disable interrupts? Don't disturb me. It's like putting a do not disturb board on the door, and the unlock function will reverse that. It will say, okay, I'm done. You can interrupt me now. So is this enough? So the answer is not always. It's not just enough to just do this in your programs whenever you want to lock and unlock, for several reasons, right? So the first thing is this disabling interrupts, enabling interrupts is a privileged instruction, and you don't want user programs to have this kind of power all the time. You don't want to give some unknown program the power to turn off all interrupts. Why? Because then it could never turn back the interrupts, right? What is the guarantee that the user won't write buggy code? For example, you could simply disable interrupts and just the program could run forever on the machine without ever enabling the interrupts. And if there are no interrupts, the operating system cannot ever get a timer interrupt and context switch it out and all of that, right? So this is a lot of power to give to a user program, which we do not want to do. And another important reason is that this won't work on multi-core, multi-processor systems, right? Because here is one thread running on one CPU and you have another thread running on another CPU. Even on this CPU, if you say do not interrupt me, then this guy on another CPU can go ahead access your shared data, right? So it is not possible for you to control execution on another CPU, another processor somewhere else. Therefore, just disabling interrupts and saying I want to run on the CPU core for a long time until I finish my critical section, saying that will not work on multi-processor systems, because even if you are not interrupted here, somebody else could be mucking with the same shared data somewhere else, right? So this idea of just disabling interrupts to lock and re-enabling them to unlock, this is useful in a limited setting. For example, in single processor operating systems, inside the operating system, inside trusted code, you can use this technique to lock and unlock. But in user programs or in multiprocessor systems, we need other solutions, right? So just remember that disabling and enabling interrupts was a primitive way of locking back in the days when all code could be trusted and you only had a single processor. So now let's go ahead and think about how we can implement locks in more general multiprocessor, user program settings. So here is a very simple idea that doesn't work. As the title says, this is a failed implementation. So suppose you have the idea that you will use a flag variable to serve as a lock, right? So anytime a process wants to lock, it will set the flag to 1, and anytime it wants to release the lock, it will set the flag to 0. So the flag is set to 1 means somebody holds the lock. And when a thread wants to acquire a lock, what will it do? It will check the flag value and it will see that if the flag is 1, what will it do? It will simply spin in this while loop. This while loop will keep on spinning as long as the flag is 1. Why? Because if the flag is 1, it means some other thread has the lock, and the thread that sees this flag is equal to 1 will keep on spinning. It will run this busy while loop forever. Not forever, but until the flag is 1. And once the flag becomes 0, it will go ahead, set it to 1 and acquire the flag. Acquire the lock, right? So this seems like a reasonable implementation of a lock, where you use this flag as a proxy to know when the lock is acquired or free, and you wait until the lock becomes free and then acquire it. So what's the problem with this? The problem is now the race condition has moved from whatever code you're protecting to the lock acquisition. Why? Suppose, let's see what happens. Thread 1 tries to lock. It waits in this loop, while loop. It's busily spinning for flag to become 0. And now what has happened? Suppose the lock has been released, right? And the flag has become 0, right? At this point, you have your flag is equal to 0 and you exit out of the while loop. You're just about to set the flag to 1 yourself, right? So at this point, an interrupt has happened. Okay, so this thread 1 has spun on the flag, realized the flag has been released, and it's about to set the flag when it has been interrupted. Now your flag is 0, your thread 2 runs, it sees there's nothing to spin, this while loop immediately finishes because flag is 0, and then it sets flag to 1 and you go back to thread 1. Now thread 1, it doesn't check flag, right? Ideally it should have realized flag is set to 1, but it doesn't check because why? When it stopped, it remembered all its registers, PC, everything indicate flag is 0. Therefore it will directly go set flag to 1. So what has happened? Both thread 1 and thread 2, both of them have set flag to 1. And both of them have acquired the lock, and both will enter the critical section. Therefore you have no mutual exclusion. Why has this happened? Your race condition has now moved to this line. to the lock acquisition part. You would have ideally wanted checking this flag as well as setting it, all of this to happen in one go, right? But that has not happened, and therefore because of that you have problems and you do not have mutual exclusion in this implementation, right? So in general it is very hard to implement locks in software that work correctly, right? Therefore you need some help from the hardware. You need what are called atomic instructions from the hardware. So these are atomic instructions that let you do multiple things like check the value of the flag and set it to something else. All of this in one single hardware instruction so that it cannot be interrupted. Using these instructions, you can build locks. For example, an example of an atomic instruction is what is called test and set, right? So what does this test and set instruction do? So here is the C code for the test and set instruction, but note that this is implemented in hardware. It is not a piece of software that you execute. This is a test and set instruction that is implemented in hardware. That is, somebody has written Verilog code for it and compiled it, and it runs on a chip, right? So what does this test and set do? It will read the old value, set it to some new value and return the old value, right? It will test the old value and set it. All of this in one swoop, right? There is no gap. You can never be interrupted between reading the old value and setting the new value, okay? So this is one example of a very simple atomic instruction that the hardware provides, and we can use such instructions to build locks. So here is a simple lock using test and set. How does it work? You have your flag variable as before, and what does the statement mean? If test and set flag 1 returns 1, what does this mean? You've read the value of flag, you try to set it to 1, and you realize that the old value is also 1. It means that the lock is held by someone else. You've set it to 1, but the old value was also 1. So in such cases, if test and set of a flag, you try to set it to 1 and you test the old value, if it returns 1, it means the lock is held by somebody else. In such cases, you simply wait. And when do you exit this while loop? Once a value of 0 is returned, right? What does that mean? It means that the flag value was 0 and you set it to 1. When that happens, then you return from the while loop. And at that point, if you were the thread that managed to set the flag from 0 to 1, the old value was 0 and the new value is 1. If that has happened, it means you have acquired the lock. And because this is one instruction, nobody can interrupt you while you run that one instruction, while you run test and set. Okay. So this is a simple way to acquire a lock using an atomic instruction. And to release the lock, it's the same. You simply set the value to, set your flag to 0. Okay. So after one thread has acquired the lock, what happens to another thread that tries to lock? Multiple threads that try to lock will all be spinning in this while loop forever. They'll keep checking. The old value still is 0, 0, 0 is 1, 1, 1, 1. Therefore, we haven't acquired the lock. They keep checking that. Therefore, all the other threads, they simply wait in this while loop. This is called a spin lock. That is, all the other threads keep spinning until they acquire the lock. Right? This is a very simple lock using test and set. So another atomic instruction that's commonly supported by most hardware is what is called the compare and swap. Okay. So what is compare and swap? Again, this is C code for compare and swap, but in real life, it is not implemented in software like this. It is implemented in hardware. What is compare and swap? You're given a memory location, you're given an expected value and a new value. And if the current value is equal to the expected value, only then you set it to the new value. Otherwise, you don't do anything and you always return whatever is the old value. Okay. So how do you implement a lock with compare and swap? So you check if the old value of flag is 0, then set it to 1. Okay. And if this compare and swap returns 0, it means you have acquired the lock. That is, the old value was 0, it matched what you expected and you could set it to 1, therefore you acquired the lock. But if this returns 1, it means you have to wait. Somebody else holds the lock. Okay? So this is a simple spin lock using compare and swap. You compare the value of flag to 0. If it is equal, you set it to 1 and you return. Otherwise, you simply keep on spinning busily. This is also a spin lock. You keep on spinning busily. If you see that the old value of flag is 1, it is not what you expect. Somebody else already held the lock, then you keep on waiting. Right? So now we've seen simple implementations of spin locks, right? So if one thread has a lock, all the other threads, they are in this busy while loop, spinning continuously and wasting CPU resources. So what is the alternative to spinning? A thread could technically check that, oh, the flag is held, the lock is held, I don't have the lock right now, and it can simply give up the CPU. It can go to sleep, it can block itself, right? So there are also implementations of locks like that. Such locks are called sleeping mutexes, right? Or in general, the default word is whenever you say a mutex without any qualifier, it means it is this kind of a lock. It is a sleeping mutex. So spin lock and sleeping mutex. These are the two types of lock implementations. So here is a simple implementation of a sleeping mutex. You test the flag. Oh, a value of 1 has been returned. I tried to set the flag to 1, but the old value is 1. It means somebody else already has the lock. So instead of just continuing in this while loop, what will I do? The thread will say yield. So yield is something like a system call. So the name may be different across operating systems, but this system call gives the operating system control back. It says, schedule me out. I don't want to run anymore. It's like the process is blocking itself. So this moves the process from running state to ready state, so that at a later point of time the operating system can schedule it on the CPU again. Okay. So this is an implementation of a sleeping mutex where a thread that finds a lock to be held goes back to sleep, gives control back to the OS. It comes back again at a later point of time. Once again it checks. If it managed to acquire the lock, it will continue to its critical section, otherwise it will give up the CPU again. And the unlock is the same. You simply set flag to 0. Right? So which implementation is good? Do you use a spin lock or do you use a sleeping mutex? So most user space lock implementations are the sleeping kind, right? Because you don't want to waste CPU cycles by spinning, right? And if one thread holds the spin lock, all the other threads of your program are constantly getting scheduled on other CPUs and they're constantly running, wasting CPU cycles and not doing anything useful. You might as well just block those threads and do useful work in some other threads, right? So in general, it is in user programs, it's better to use the sleeping mutex, though you can also use spin locks. There's nothing against it. Now, that is about user space programs. What about inside the operating system? Operating system code also needs to use locks to protect from, there could be one process in kernel mode on this core, another process in kernel mode on some other core, right? Both of them could be accessing the same shared data. Therefore, you need locks. So for operating system code, what type of lock should you use? It turns out that you can only use spin locks. You cannot use a sleeping mutex. Why? So if operating system code says yield, who's going to take care of the hardware, right? So the operating system has to always run. A user space program can say yield and say, I don't want to run some other process. But the operating system can never say yield. If the operating system sleeps, who's going to wake up, right? So the operating system is the default software layer that's running on hardware. Therefore, inside the operating system, it doesn't make sense to yield the CPU to somebody else. Therefore, inside operating system code, spin locks are your only option. Okay. So kernel code always uses spin locks to protect shared data structures. Okay. So we've seen before operating system code on single processor systems. It was enough to simply disable enable interrupts. But On modern multi-processor systems, all operating systems use spin locks to protect shared data structures. And when the operating system acquires a spin lock, when you're writing kernel code and you acquire a spin lock, you must take certain precautions. So first, acquiring the spin lock must always disable interrupts on that particular CPU core. This doesn't guarantee mutual exclusion, but it'll help avoid complications. For example, you have acquired some lock and then you get interrupted, and the interrupt handler also requests for the same lock. Then what will happen? This lock is held and somebody else is requesting for the same lock, and this lock is going to spin forever and you're never going to go back, right? You're going to have all sorts of deadlock situations that happen. Therefore, when you hold a spin lock, it's always good to disable interrupts so that nobody else could request and spin for the same spin lock, right? And similarly, you must also not perform any blocking operation when you hold the spin lock, right? When you're holding the spin lock, you should in general take care to just finish your work as soon as possible, finish updating your shared data as soon as possible and release the spin lock. Because while you're holding the spin lock, if you get interrupted, if you block, if you stop for whatever reason, then somebody else will come and they might request the same spin lock and they will keep spinning forever. The control will never come back to you to release the spin lock, right? So you hold the spin lock, you sleep, somebody else is waiting for the spin lock, they don't give up the CPU, you can't release the lock, and it is a classic situation of a deadlock. Therefore, when you acquire a spin lock, you have to be very, very careful when you write code that acquires a spin lock inside the kernel. Take care, release it as soon as possible, and never do anything that can block or interrupt, right? So if you're developing kernel code, this is sort of very important stuff to keep in mind. But in user space programs, if you're writing C programs that use the pthread locks, you don't have to worry too much about it, because you can always use the sleeping mutex and you can hold a lock, the other threads are sleeping, you can take as much time as possible with the lock. It's not going to result in something dangerous like deadlocks. So how should locks be used? Finally, we'll just end with basic guidelines. So anytime you have multiple threads in your code and you have any shared data, counters, data structures, stacks, heaps, links, a linked list, whatever, anytime you're accessing these shared data structures, you must always hold a lock so that concurrent accesses to the same shared piece of data do not happen, right? So such implementations of data structures, such implementations of operations on data structures are called thread safe data structures. So if a linked list implementation provides you insert delete functions and it says it is thread safe, it means that internally the insert delete are all using some lock, so that if multiple threads also call the same functions, mutual exclusion is guaranteed, right? In user space programs, you should either use locks yourself or use thread safe implementations of other data structures from other libraries. And inside kernel code also, all shared data must be accessed only after locking. And you have two different philosophies of how you can lock. You can either have coarse-grained locks or you can have fine-grained locks. What is this? So coarse-grained locking means you have, if you have a large linked list, you have one big fat lock for the entire linked list. And any operation you want to do anywhere in the linked list, you take this lock, you do the operation, and then you release the lock. On the other hand, fine-grained locks are, as you can see from the name, probably every element of the linked list has a lock, right? So that you only take the lock for that part of the linked list that you want to edit. So fine-grained locks obviously allows more parallelism. So if you have, a linked list like this, you could have one lock here, one thread executing here with one lock, another thread executing here with another lock, right? You could have some sort of parallelism that is happening. But at the same time, you have to be careful. You have to manage all of these multiple locks, and so fine-grained locking is better for performance, but it's a little harder to do it correctly. On the other hand, coarse-grained locking is easy. You just take one big fat lock for everything and release it when it's done, right? And finally, one last thing to remember is all of these libraries, the operating system, all of these provide locks to user programs, but it is up to the user programs to develop a correct locking discipline, right? It is up to you to be careful in acquiring locks, releasing locks, and so on. The operating system itself, simply because you're using pthread locks, doesn't mean it is always correct. You still have to make sure you take the lock and release the lock correctly.